Hello everyone. In this video I'm going to show you how to simulate conjugate heat transfer and two-phase cooling using ANSYS Fluent. In this simulation we will use a volume of fluid method as a two-phase model simulation, as well as conjugate heat transfer at the same time to cool an object, as you will see. First, let's create a 2D geometry. I will use a 2D geometry to expedite our simulations. So let's do the units as millimeters. So here, let's create rectangular. So it's 50. Let's do the 80. Okay. Then let's define an inlet and outlet for this one. So let's go create another rectangular here and one here. So let's modify the dimensions. Okay, let's do horizontal. Let's define this one as 15. Size of this one is, let's do, for example, 18. And here with 12. Oh. 12. And same here. 12. 18. Let's make this one a little bit longer, like H2. Like, let's make it 120. So maybe 100. Okay. Then we need to cut these out to make them one piece. We'll go to modify, trim, and okay, we'll delete these lines. Okay, so this will be our one domain. Let's go to modeling and create another sketch, like circle. Let's do somewhere here. Like something like this. So we will do like in the air we will have a water falling or spraying on this object and cooling it down. So let's define this one, the diameter as, let's do 30, and we need to define this distance between these two. So let's do the 24, so it will be in the middle of this one, and I think that's fine for now. So let's go to the modeling part to create our objects. So for the first sketch, create concept, surface from sketch, apply, generate. And for the next sketch, we'll select the sketch number 2, again concept, surface from sketch. We'll apply, if we use the add material, it will merge both of them to one part, so we don't want to do that, so we'll do add frozen. It's kind of will create a new part, like overlapping each other. So since they are overlapping, we need to separate them. So we'll do create a boolean, and we'll do subtract. The target body is this one, the tool body. So when you click here, you need to click this one to select the circle, then preserve the tool body. We'll say yes. So generate. So as you see, you'll have two parts. One is the air, outer surface, and the other one is the circle one. So we'll select these two and form a new part. So it's very important to create, put those two bodies in one part when you are creating your geometry. In this case, when you mesh it and import it to the Fluent and do the conjugate heat transfer, you do not need to define the interfaces manually. They will Fluent will take care of it automatically when you create a single part. So that's very important. So let's just air body, rename these, and let's say as circle body. Okay, then this one is Floyd, and we can do that here or later in the Fluent, so I will do it here. So I will close this one, the geometry, and open the meshing. It will take a while. Okay, now we have our geometry here in the meshing. So what will I do first? Let's do a small mesh to see what's the automatic setting and what was the first mesh we will see. So this mesh, for this tutorial, I want to do a very fast simulation to just show how it's gonna be done. But if you are going to, for example, calculate the heat transfer coefficient on this surface, you need to add inflation layers. You need to have a more finer mesh around this object, and based on the higher gradients, the places you have higher gradient, finer mesh to capture the boundary layer and those kind of stuff, which is a different topic. But for this one, I will use this mesh. You can see the let's check the quality and go to mesh metrics, skewness. The maximum skewness is 0.5, which is very good, and orthogonal quality, the minimum is 0.7, so something like 0.2 is 15 to 0.2 is acceptable. So I will keep this mesh. So now let's define our inlet outlet kinda. I will click here and press the button N, like you see, create new name selection N. So I encourage you to use the shortcuts, so it will be faster. So I will define this one as inlet and click this edge and define this one as outlet. Then I will go to the surface selector, select this object and define as, let's say, circle. Cool. And this one as the air. Okay, now we have all of the name selections. These are surfaces, the inlet and outlet here. So I will go and update the mesh, so it will send the information to Fluent. So let's close the meshing and start the Fluent. So I will go, this is by default 3D, I will use parallel mode to expedite. I have 8 processors on my computer, and I have the MPI of Intel. So let's just start the Fluent. Since we have a very small number of mesh, it should be very fast. Okay. Now we will do transient simulations. Then let's define the materials first, because I'm gonna use volume of fluid. So if we have the second fluid phase, that will be automatically assigned. So let's go down and select water, copy, close, close. So you can see in the material we have 2 fluids now. Let's double click on the multi-phase and select volume of fluid. Let's do the implicit, sharp, interfacial anti-diffuse and implicit body forces. So click OK. So we have phases here. Primary phase is air, to make sure that we are having like right names based on the material. I will rename these phases so later we can refer to them easily. This is this doesn't have any impact on the simulation results, it's just for convenience. Then turn on the energy equation. Okay. And for the viscous model, let's go click K epsilon, realizable K epsilon model. So I will keep the standard wall function. Okay. Then let's close this one. Okay, cell zones. So air is fluid and circle is solid. This is important to make sure that these names are based on our name selections. We selected the bodies, if you remember, in the mesh, so it's easier to identify. But if you forget to name them, so it's easily just right click on it and display. So it's showing the air, and right click here on display, this is showing the circle. So you can check that you are defining the solid and fluid zones correctly. So display the mesh again. So let's go to the boundary condition. So for the inlet, let's do 0.1 meter per second, and for the temperature, let's change the units of the temperature to Celsius. Close. I want to have a water from inlet at 20 Celsius. So let's click OK. So for the inlet, this is a 2-phase model, so we want to make sure that everything is coming from the inlet is pure water, no air in it. So double click on the water and define the volume fraction of the water as 1. So in this case you will make sure that you are having only water spraying from inlet. If you have a different case, you can do 50-50 or whatever volume fraction is proper for your problem. So I think that's all for the boundary condition, I have just one inlet. The outlet is defined automatically because we name it outlet. It's a pressure outlet. Then let's go to the methods. So I will use the non-iterative transient model with bounded second order for the time and second order for all of these. Then let's go to the controls. So the relaxation factors, let's do 0.2 for pressure, maybe 0.5 for momentum, this is for the K, 0.5, this is for the epsilon, 0.5. Then go to the advanced. Let's do these 7. Okay, these are for, these parameters will help our convergence. So these are under relaxation factors. You can refer to Patankar's CFD book and read more about these. That they are there's a very good definition and very good explanation on these in that book. So let's do a report, create a report graph. So let's go area weighted average, or we can do let's do the area weighted average of temperature on the circle. So we want to report the plot every one time step, and we can do circle underscore temperature. Okay, and we can check this one to have the file, and or print to console will print here. So I will go with the plot only. Then okay, close this one, and let's initialize our case. Then let's see, I wanna initialize everything is at 25 Celsius. Then I wanna patch, so kinda initializing one part differently. I will do create temperature of the circle at 100 Celsius. So click patch. So we can see, let's do the counter one, will be the temperature of the air and circle both together. Let's display this one, so you can see that everything is at 25 Celsius and this circle is at 100 Celsius. So let's change the numbering here as a float with one digit. Okay, it's better now. So you can see that everything is at 25 Celsius, the circle is 100 Celsius. Okay, let's close this one. Let's create another counter. Let's do phases, volume fraction of water in both of these. So you can see there's no water here, and inlet is showing some part because we defined 1 for the inlet, pure water. Then let's define this one as T circle. So counter of temperature on mixture will be total temperature circle. Okay, 100. Another for volume fraction of water in air only. So I will show why I'm doing this. So let's create a scene with temperature of the circle and volume fraction, and save and display. So it will have two. Okay, let's do float. Let's do one. So this will be better. So for the scene, I will create an animation showing temperature of the circle and volume fraction of the where is the water here, and our area of the interest is the temperature of the circle. Okay, then go to connection, calculation activities, create solution animation. I will create 3 animation every 10 time steps, with one from counter 1, another again every 10 time steps on counter 2, and the third one will be again 10 time steps from scene 1. Okay, now we can go to the run calculations. I will use the adaptive time step size and the total time of the simulation. Let's go to 15 seconds or something like that. Do the setting, the minimum time step 10 to the minus 5, the maximum, let's do the 0.5. Save. Let's keep the courant number as 2, so it will be slower, but we will not have convergence, and we'll have better accuracy. Also, I will go to the calculation activities and save the results every 100 time step. Okay, so let's go to the calculation and report simulation status. So it will show everything here. So let's click calculate. So as you can see, first we will have 3 animations. This is the temperature of the circle, so you can see it's starting to heat up the surrounding air, and we have no water reached here so far. So, and because it's a very like 0.02 or 3 seconds so far, so and you can see that the water is moving down. So, and the circle is heating up the air, but when as soon as the water reaches the circle, you see temperature drop is just 0.1 Celsius so far, but you see that the big sharp drop in this temperature graph. You can see that water is reaching the top of the circle, and it will start cooling down this circle. So I will stop the video here because it will take for a while until it's finished, and come back with the results when it's finished. Okay, now the simulation is completed. We can see the simulation results. Let's expand this part a little bit. So if you can see from this temperature profile, in 15 seconds it dropped like almost from almost 40 Celsius, from 100 to 60. So if you see the temperature, you can see that the red one is now 60. So this is the temperature animation with the volume fraction. If you go to the animations here, let's close this one. If you go to the animations here, animation playback, select the third animation. So let's uncheck this one. and zoom a little bit here. So let's play this animation. You can see how this one is working and cooling down from the top. So this is kinda putting together the volume of fluid VOF two-phase simulation with conjugate heat transfer, which is very useful in spray coolings and different kind of engineering applications. So I hope this is useful. Also, if you remember, we saved our simulations using save our results in solution calculation activity every 100 time steps. We can go to the post-processing part and see the results and animations there. So we can wait until it's saved. We can open the CFD post. And we can see different counters, for example, counter of volume fraction of water here, and another counter circle temperature. So you can see the local temperature, how temperature, like top part is colder than the lower part, how the part is water is flowing is colder than the lower part. So I hope this was useful. Please like our videos if you like them, subscribe to our channel, share with the fellow colleagues, and if you have any question about the simulations, or if you have any problem with simulation with, please leave us comments, so I will try to do these simulations based on your requests. And thank you for watching, and bye.